Well, let's go ahead and get started. So we're going to start with Sarah Gabala from Ruhr University Bochum, and she's going to tell us about Anonify, Decentralized Dual-Level Anonymity for Medical Data Donation.
Hello everyone. My name is Sarah Gabala. I'm from Ruhr University Bochum, Germany, and I will present to you our work, Anonify, Decentralized Dual-Level Anonymity for Medical Data Donation. So medical data donation is a voluntary act where individuals share their medical data with researchers to support scientific research. Medical data donation has gained a lot of attention recently, especially during the corona pandemic, with many applications have developed to facilitate data donation. However, medical data donation faces challenges, especially due to the sensitive nature of medical data. So to encourage users to donate their data, we need to ensure privacy to them. Anonymity is known as one of the most popular privacy protection methods. It ensures that each individual cannot be identified from K-1 other individuals. So to achieve anonymity, a dataset should be modified to or by removing direct identifiers like names and generalizing quasi-identifiers like age to create groups of users who are similar in terms of quasi-identifiers. And by doing this, we protect sensitive attributes, like here in our example, disease. One of the main advantages of anonymity is its ability to allow flexible analysis, so it doesn't assume exact usage or the exact studies that the researchers will conduct. And of course, this is good. However, anonymity requires a central trusted aggregator. That means the user should trust one entity for aggregating the data and also for learning who donated what. Another problem with anonymity is its vulnerability to attribute disclosure attacks. And so as we can see in the second group here, that all records have the same disease. So if an adversary knows that specific person has a record in this group, then the adversary can know that this person has HIV. There are solutions for this issue. However, these solutions still require centralization. To address these limitations, we propose our protocol, Anonify. In our protocol, the responsibility of the aggregator is distributed over several servers, where one of the servers should be honest. Anonify achieves privacy protection at both the communication and data levels, so it achieves dual-level anonymity that ensures users can be linked to their donated data through communication metadata like IP addresses or through characteristics in the donated data itself. We assume a global adversary who can observe the whole communication, and also this adversary can collude with servers responsible for aggregation or researchers. Additionally, it can have background knowledge about some users. In our protocol, we use distributed point functions. It's a method for enabling anonymous writing in a distributed database without servers linking user to specific messages. So to write a message in this database, the user should generate several secret shares and distribute these shares to the servers, where each server gets one share. The server should add the share to its database instance. Then, after collecting or processing requests from several users, the servers collaborate together to compute combined data and reveal the written messages. For data anonymity, we rely on two methods, key anonymity and stratified sampling. We use stratified sampling to address the limitations of key anonymity. Both methods are executed within secret sharing settings. So stratified sampling, it ensures that an adversary cannot determine the presence of a user's record in a published data set, and that is by deleting fixed number of records from each group. That adds a level of uncertainty. Our approach consists of two phases. The first phase, registration phase, where the users send their personal information, the quasi-identifiers values, and then the servers collaborate together, work together to apply key anonymity to these identifiers, and then they create classes, broadcast the information about the created classes to the users, and then each user determines the related group. After users complete the registration phase, they move to the publishing phase, where they share their medical data, of course using the DPF, also alongside with the group ID. Then again, the servers work together to apply certified sampling, but before decrypting the database. So they agree on which rows should be deleted from the database instance, and then they combine the database instance to reveal the sampled or the anonymized data set, and finally the aggregator publishes the sampled anonymized data set to researchers. In our evaluation, we use a public diabetes dataset, and we use ERX for canonization, because based on our evaluation that ERX provides better utility than other methods. And for the key value, we use 250 because, also as shown in the results here, it maintains good utility, and of course it ensures big anonymity set. We assess the likelihood of linking a specific record in the dataset to a targeted user, and as shown in the results here, all the anonymized datasets have very low values that indicates strong anonymity and low re-identification risks. Also, we assess the performance of machine learning classification algorithms on the datasets anonymized by our protocol, and as you can see, the accuracy of the anonymized datasets are close to the accuracy of the original dataset. Also, another thing we assessed is the impact of anonymization on the data distribution. Again, here the anonymized datasets closely resemble the original dataset. So in conclusion, we proposed Anonify. It's a decentralized protocol for medical data donation. It ensures a strong anonymity protection without relying on a single entity. According to our results, Anonify maintains data utility, so it ensures that machine learning algorithms perform nearly as well on anonymized datasets generated by the protocol as they do on the original dataset. If you would like to know more about our paper, because we provided more results, also we provided detailed security analysis, so you can read our paper. Also, we provide the artifacts, so you can check it. Thank you.
And yeah, we have time for questions. And just raise your hand and they'll bring a mic to you.
Thanks for great speech. I'm wondering about is there only is only one person will be represented as a one record considered for the comorbid or something, so the disease will be what kind of the disease will be recorded? And finally, the most interesting about is the why you do the stratified sampling, especially the different different subgroup have the different disease distribution. So how did you consider this kind of impact? Thanks.
So you mean that each user will have
Only
one record? Yes, but also we support multiple iteration, so the user can submit at a different interval of time. But using certified sampling, we prevent an adversary from being sure that the user has a record in this dataset.
Okay, and we have time for more questions. And yeah, let us know if there's any questions online.
Is it on? Okay. I have one question. In your overview slide, you showed that at some point data is decrypted, but I did not see where it is actually encrypted in the first place. Can you explain?
As I mentioned, so here, as mentioned, they submit their data using DBF, and that means that it's a secret sharing based protocol where there is a much share service.
Okay. I don't see any other questions, but I had a question about the distributed point function. So can you say more about the, because I remember in the paper there were more details about how that happens, like actually over the network with anonymity and everything. Can you say more about that?
You mean the performance or for the anonymous communication aspect?
Yeah.
Yeah, so we didn't provide this, but we provided some information about this in the in our paper. So according to many papers, DBF doesn't lead to high latency, and this is good. Although we don't really care about latency here in this context because this scenario can tolerate some level of latency. Another thing, which is the bandwidth overhead. And we provided some details about the bandwidth overhead. And since the user don't send many messages or they don't exchange many messages, still the overhead is limited. But it's related somehow to the database size also. So if you are interested, you can read more about this.
Okay, and we have time for one more question if there are any more questions. But, if not, let's go ahead and thank Sarah one more time. Yeah, great.